Okay guys, so we studied the following function. It has been given us the function of the exam of February 2018. Okay, so let's consider f of x equal to the logarithm of the absolute value of so we have log of the absolute value of cubic root of x plus 2 close the absolute value and plus the cubic root of x. Nice. So here is the function. As usual, the first question is find the domain, symmetry properties, limits, boundaries points, the boundary points of the domains, and if the boundary point and the asymptotes if you have some asymptotes. So let's go first and try to find the domain of the function. Here let's say that to get the domain, I remind you that there are no condition on if I have the n root of quantity. If n is even, I don't have to set the condition that the quantity should be greater or equal to 0, right? So when I have cubic root of x, there is no condition on the arguments of the quantity inside the cubic root of the arguments, okay, of the cubic root. But I have the logarithm. But if you have logarithm of absolute value of quantity, then you should ask the quantity should not be equal to 0, right? So here the condition for the domain is that the cubic root of x plus 2 should not be equal to 0, right? So we get that the cubic root of x should not be equal to minus 2, and thus we can cubic root of the we can put all the sides both the sides to cubic root. So we get that x, so I cubic root of x all cube should be different than minus 2 all cube. The cubic root of x all cube is x, should not be equal to minus 8. Okay, so this is claiming that our domain is R except minus 8. Thus it is from minus infinity till minus 8 union minus 8 till plus infinity in minus 8. Okay, nice. This is for the domain. The second question we want to address is the symmetries. Please note that cubic root of minus x is basically minus cubic root of x, but this thing will not help us here, because if you are thinking that f of minus x is minus f of x, it is wrong. Okay, so here there are no this function is not even and it is not odd. It's not even and it's not odd. Why? Because if you try to do f of minus x will just be the logarithm of the cubic root of minus x plus 2, there is the absolute value here, okay, plus the cubic root of minus x. Nice. Here you will say, okay, good, it is the logarithm of minus cubic root of x plus 2, okay, then minus cubic root of x, but this stuff is not minus f of x, so the function is not even, it's not odd. Okay, it's not odd, it's not even. And the last question is about the limits and the asymptotes. Let's try to get the limit of the function. If I do the limit when x tends to minus infinity, it will be, so going back we will see that if I put minus infinity, it will be cubic root of minus infinity plus 2, okay, it will give me a plus infinity, the logarithm of plus infinity, no, it will be giving cubic root of minus infinity is minus infinity, plus 2 will give minus infinity. The logarithm, we put the absolute value, it gives plus infinity. The logarithm of plus infinity is plus infinity, and plus the cubic root of minus infinity is minus infinity. So if I try to do it at minus infinity, so let's write it. it will give us the logarithm of the absolute value of the cubic root of minus infinity plus 2, okay, plus the cubic root of minus infinity. But keep in mind that this will give logarithm of at the end, because you have cubic root of minus infinity, which is minus infinity, plus 2 is minus infinity. The absolute value give it plus infinity, and here this is minus infinity. So we will get plus infinity minus infinity. This is as usual an indeterminate form. Okay, this is an indeterminate form. But how do you, but believe me, so from one part this is a logarithmic infinity, okay, whereas this infinity here, so basically this is a you have a logarithmic infinity, this part here, and here you have kind of, it's not a polynomial, but it is x to power 1 over 3. So this infinity here is more powerful than this one. Remember that the logarithmic infinities are always let's say are the weakest one. I don't know if you say weakest, but I think what is the worst one. So they are very slow. Logarithmic infinity are very slow. So the most important one here will be cubic root of minus infinity, and thus the limit will be minus infinity. Is that clear? The same when doing the limit when x tends to plus infinity, you will get the log. You do the computation, but you get log of plus infinity plus plus the cubic root of plus infinity, which is plus infinity. In this case, it is plus infinity, and you will get plus infinity. Excuse me. No, here, no. I'm coming back with the. So now we remain with the limit when x tends to minus 8 minus. Okay, so we go and substitute minus 8 in the function. If you substitute minus 8 in the function, you will get that. Please let me use this pen. We get logarithm of the absolute value of cubic root of minus 8 minus this minus 8 minus minus 2. No, I mean plus 2. Yes. Then my plus yes, the cubic root of minus 8. Now what come out, it gives you the logarithm of the cubic root of 8 is 2. The cubic root of minus 8 is minus 2. But you are doing the cubic root of something of minus 8 minus, so you are still to reach minus 8. So this will give you 2 minus. Yes or not? If there is any doubt, please write me in the comments. And plus 2, so this is minus 2, excuse me, minus 2 minus plus 2. Okay, and then here is the absolute value plus here the cubic root of minus 8 is minus 2, so this should, okay, so it gives you logarithm of minus 2 minus, it means that you have minus 2 here. Minus 2 minus means that you are to this side, so minus 2 minus will be minus 2.0001. So if I do minus 2 minus plus 2, it will be minus 2.001 plus 2, it will be 0 minus 0 point something, so it's a negative 0. By the way, I don't care, there is the absolute value, so I will get the logarithm of 0 plus minus 2, but the logarithm of 0 plus is minus infinity, right? Doing the same, you will get that the limit when x tends to minus 8 plus will also be minus infinity. Okay, because by the way, you will get the logarithm of 0 plus and a number, so it will be minus infinity. To summarize, we can now we got all the limits, and we can talk about the asymptotes. So a vertical asymptote, yes. Why? Remember that we have vertical asymptote if there are some point in which the function goes to infinity. In fact, we saw that when x tends to -8, the function goes to infinity. So x equal to -8 is a vertical asymptote. Then, do we have horizontal asymptotes? The answer is no. We don't have horizontal asymptote, because to have horizontal asymptote, the limit of the function when x tends to +infinity or to -infinity should be a number, and it's not the case here. Do we have oblique asymptotes? Also here, the answer is no. Why? I don't even need to check, because look, when you look at this function, the function to have an oblique asymptote should be equivalent to a line when x tends to infinity. I repeat, the function to have an oblique asymptote should be equivalent to a line when x tends to infinity. But in this case, we have the function that is logarithm of cubic root of x -2 +2, okay, plus cubic root of x. Please note that the logarithm is not so that powerful. So the principal part of the function, we can say that f of x is equivalent just to cubic root of x as x tends to +infinity or -infinity. But the cubic root of x is not a line. Okay, so when the function is not equivalent to a line when x tends to infinity, this function doesn't have the oblique asymptote, so it's useless to check. You will not find it. Okay, so now we have done with the first questions. I will just okay, so we got I moved to a new page and summarize all the important results. So moving to a new page, we will say that the function we are studying is f of x equal to the logarithm of the absolute value of the cubic root of x +2 plus the cubic root of x. Then we saw that the domain of the function is from -infinity to -8 union -8 to +infinity. Then we saw that the limit when x tends to +infinity is +infinity. The limit when x tends to -infinity is -infinity. The limit when x tends to -8 minus is the same as the limit when x tends to -8 plus equal to -infinity in all cases. And we saw that we have x equal to -8 like the vertical asymptotes, and no horizontal asymptotes, no horizontal asymptote, and no oblique asymptotes. Nice. So this summarizes what we did so far. Now we go back to the exercise to get the next question. The next question says, study the differentiability of x in each point of the domain and compute the derivative. So look, the question first says you need to study the differentiability, then compute the derivative. Okay, so first you study the differentiability, then you compute the derivative. Please note, anytime you have n root of f of x, the point where you have to study the differentiability are the root. So when you have n root of f of x, the point where we have to study the differentiability, you have to study the differentiabilities, to study the differentiability at the point where f of x is equal to 0, at the points where f of x is equal to 0. So if you have this n root of some function, the point suspect the suspected point, the point that where the function may not be differentiable, are the point where f are the root of f of x. In our case, we have the function f of x equal to the logarithm of the cubic root of x plus 2 in absolute value plus cubic root of x. So we just need to, with this function, the only function inside the root is x, and x is equal to 0 only when x is equal to 0. We need to study the differentiability in x equal to 0. Usually people first compute the derivative and then study, but in this case they ask us to study the differentiability in 0. To study the differentiability in 0, we do the limit when x tends to 0 of f of x minus f of 0 divided by x minus 0. Thus we do, in this case, f of x is what? So it's the limit when x tends to 0 of my function, which is logarithm of the absolute value of the cubic root of x plus 2 minus cubic root of x. If you what is f of 0? F of 0 means that I should put 0 in the function. So minus, if I put 0 in this function, it will be the logarithm of putting 0 in the function. I get logarithm, it will be logarithm of 2 minus 0. So putting 0, it will give me the log of 2 divided by x, right? Need to find down these limits. Okay, so how do I find this limit? Keep in mind that if it is like a kind of 0 over 0, the limit is 0 over 0, because if you substitute it, so it's an indeterminate form. This is the stuff. So to find it down, okay, keep in mind that, okay, they say study the differentiability and then compute the derivative. But if you are not able to do what I am doing now, it's better for you, maybe you compute the derivative and then you study the differentiability. Okay, so please note that when I have a cubic root of x plus 2, when x is tending to 0, okay, when x tends to 0, cubic root of x plus 2 is a positive quantity, because, by the way, this is 0 and this is 2, and it means that the absolute value of cubic root of x plus 2, as it's a positive quantity, will just be cubic root of x plus 2. This whole when x tends to 0. So this limit can be written like the limit of cubic root of x plus 2 minus this here is plus for the function, plus cubic root of x, okay, minus the logarithm of 2 divided by x. This is the limit I am solving. Please note that I can split this limit in 3 parts. Like it will be the limit of the cubic root of x, the logarithm divided by x, plus the cubic root of x divided by x, plus the logarithm of 2 divided by x. Okay. Now, if I remind you that x is tending to 0. So suppose that we first do at 0 plus and then we will do at 0 minus. So if you are doing at 0 plus, if I put 0 here, okay, if I put 0 here, what happened? If I put 0 in the, no, this is minus, excuse me. If I put 0 here, I will get ln of 2 divided by x, okay, minus if I put 0 here, yes, I get ln of 2 divided by s So this will be len 2 divided by s plus root 3 of x over x minus len 2 divided by x. Right? So this and this cancel and remain with cubic root of x divided by x. Yes or not? That is 0 over 0, but it's x to power half 1 over 3 divided by x. That is x to power 1 over 3 is and that it become 1 over x to power 2 over 3. Yes or not? Because we take this 1 over 3 down, so it gives you 1 over cubic root of x squared. And so if you do the limit when x tends to 0 of this, it will just give you 1 over cubic root of 0, okay, which is 1 over, because it's x squared, so this will be 0 positive, independently if you are doing 0 minus or 0 plus. 1 over 0 plus, that will be plus infinity. So we got that f prime of 0 is plus infinity. So I mean it tends to plus infinity. So f is not differentiable to both the sides. So f prime of 0 give plus infinity to 0 minus, and the same to 0 plus, because as I said here, independently if you take 0 minus or 0 plus, this is the x squared. So 0 minus or 0 plus, it will by the way give you 0 plus. Okay, and when the derivative from the right and from the left give the same, okay, is that clear? This is a vertical, so x equal to 0 is a not differentiable point first. It's a not differentiable point, and we say that at this point, as the derivative from the right and the left gave the same thing and they gave plus infinity, we say that x equal to 0 is a vertical tangent point. Nice. I repeat, if you are not able to do these steps, please do the derivative and then do the limits on the derivative. Okay, so now that we know at which point the function is not differentiable, that at 0 we need to compute the derivative. The function is f prime. Let's say f prime of x is f of x equal to the logarithm of the absolute value of cubic root of x plus 2 plus cubic root of x. This means that I remind that if I have the logarithm of absolute value of f, the derivative is just f prime over f. Okay, and so turning back to this, my derivative will be the derivative of this. So f prime of x will just be, I need to derive this. Okay, so what is the derivative of cubic root of x? The derivative of cubic root of x is 1 over 3x to the power 1 over 3 minus 1. Okay, plus the derivative of 2, which is 0. So this is divided by the cubic root of x plus 2, then plus the derivative of cubic root of x, that is 1 over 3 x to power 1 over 3 minus 1. So let's write better the derivative. It's f prime of x equal to 1 over 3 multiplied by x. 1 over 3 minus 1 is minus 2 over 3, right? X to power minus 2 over 3 divided by the cubic root of x plus 2 plus 1 over 3 multiplied by x to power minus 2 over 3. Okay, so then one get that f prime of x is equal to you can easily see that we can bring out the x to power minus 2 over 3. So we can take x to power minus 2 over 3 out. Here we remain with 1 over 3 all over cubic root of x plus 2. Right? No, we can even bring 1 over 3 because we can, and here we remain just with 1 and plus 1. Okay. So this is our so let me write the derivative in another page. So it's just the derivative is f prime, excuse me, is f prime of x equal to 1 over 3 times x to the power minus 2 over 3 multiply by 1 over the cubic root of x plus 2 then plus 1. Yes. Okay, so that one can write it like just because we don't like to write a power with fraction, is 1 over 3. This x to power this is x to power minus 2 over 3. Okay, it is like you can, if you send it down like this, it becomes x to power 2 over 3 multiply by 1 over cubic root of x plus 2 plus 1, right? And so finally it gave us 1 over 3. X to power 2 over 3 is cubic root of x square multiply by, let's put to the same denominator, it will be 1 plus cubic root of x plus 2 divided by cubic root of x plus 2. So these are just the steps to f prime of x. I am just writing the derivative so that then we can directly study the sign. Okay, 1 over 3 cubic root of x square multiply by 1, so 3 plus cubic root of x divided by cubic root of x plus 2. So now this is the final form of the derivative that we got. Okay, so by the way, you are not required to do all this step when somebody asks you to find the derivative. Okay, but when you are not required to do all this step when somebody asks you to find the derivative. But when you will be asked to study the monotonicity of the function, you are obliged to do all these steps, to write the derivative in such a way that you can study its sign. Otherwise, you will not be able to study the sign of the derivative and thus do the monotonicity. Okay? So when you these are the steps, by the way. Okay, going back to, excuse me. So we then say find the monotonicity interval of and maximum minimum points. Say if they are relative or say if they are relative of absolute. So we need now to study the monotonicity. So studying the monotonicity means I should study the sign of this function. Please note that the sign of this part here, it's always positive, right? It's always positive. Whereas this but we need to study the sign of the order components. So we have the component 3 plus cubic root of x that we want it to be positive. It means that cubic root of x should be greater than minus 3. We can cubic root both the sides, so I mean cubic root of x all cubic. Oh no, we can cubic we can take it all the sides to cubic, not cubic root of the sides. Okay, so x Okay, this should be this greater, so x should be greater than minus 27. Okay, so this part here is positive when x is greater than minus 27. The other part we want to study is this part, cubic root of x plus 2 greater than 0. It happened we can do the cubic root to all the sides. First of all, we write cubic root of x greater than minus 2. We put the cubic roots above the side and it gives you x greater than minus 8. And we put the cube in, we take all the sides to the cubic power. Okay, then we have all the elements to study the sign of the derivative. Now let me study the sign of the derivative here. So the derivative will be like this. We have x, we write down all the domain here, minus infinity. We also saw that minus 8, but we also saw 0, which was the not differentiable point, and there are many other points that we saw minus 27 also. So let me cancel and put it, I forgot. So we saw that the important points that we got was minus 27, minus 8, we saw 0, and finally plus infinity. So the derivative, there is the first piece, which is this one, this piece here that I say is always positive, but let's put it in the table anyway. 1 over 3 cubic root of x squared is the first piece of the derivative. The other pieces are 3 plus cubic root of x, and the last piece is cubic root of x plus 2. And finally here we have f prime. So what is the then we split, we put 2 bars because the function is not defined, and we split. Okay, so then we have that here the function is always positive, the derivative is always positive. Now we saw that 3 plus cubic root of x, 3 plus cubic root is positive only when x is greater than minus 27. So here it goes to 0, and then when x is, so here it is negative, then when x is greater than minus 27 it becomes positive. This happened the same for this guy. When x is greater than minus 8 it becomes positive. So minus 8 is here, so we get negative, negative, then positive. At the end the derivative is negative, so plus times minus, so it gives you plus, here minus, here plus, and here plus. Okay, so it means that if we add here the function f of x, I remind you that the limit at minus infinity was minus infinity. Then we need to find f of minus 27. So the function increased from minus infinity to f of minus 27. Then from here it will decrease to, I remind you that the limit at 8. So no, but it's better maybe to do it on another table. Let's do the f on another table. By the way, oh no, make it crazy. Okay, so we'll do let's do another table for the function. So the other table we do is the same scheme, like x minus infinity, minus 27, minus 8, minus infinity, minus 27, minus 8, 0 plus infinity. Then we just put the derivative f prime, here the two bars. Okay, nice. So the function was the derivative was positive, negative, positive, positive. So it means that here, as I said, the function, the limit at plus and minus infinity was minus infinity, and from here it increased to f of minus 27. Then from here it decreased to minus infinity because the limit here, and they are, remember also that the limit at minus 8 minus plus was minus infinity, and from that it increased to f of 0. Then from f of 0 it increased to plus infinity. Okay, so one can directly see from this table that the monotonicity is that f is increasing in you can see that the function is increasing in the intervals minus infinity to minus 27, and it is also increasing in the interval from minus 8 to let's say minus 8 to plus infinity, right? Because here I can combine the interval because it is continually increasing. If you are not confident, you can say from minus 8 to 0 and then from 0 to plus infinity, no problem. Okay, then it is decreasing just in the interval from minus 27 to minus 8. Okay, now we can directly see from this table that x equal to minus 27 is a local or relative, if you want, local or relative maximum point. Okay, yes, it is a maximum because the function do like this, but it is just local, or because the function then goes to plus infinity. It's the maximum but not the highest point in the form of the function. And one can clearly see that there is no minimum point, right? There is no minimum point. Okay, nice. Next question says, okay, trace the qualitative graph of the function. Okay, here when you are here, basically you have done, because here on this table you can see the graph. The function goes up, then come down, is the asymptote, then it go definitely up. Like, let me draw it here. We need, so here we have, let's say that this is minus 8 and this is minus 27. Okay, I think I can cancel this table, by the way. It's no more useful. It helps us a lot, but now thanks. Okay, nice. So to get some space. So here is minus infinity. Now you see that we have the point minus infinity, that says here is also minus infinity on the y-axis, and here is plus infinity. Minus infinity means that we have this point here, and then we have the point minus 27, f of minus 27. One has to go and compute f of minus 27. I remember that the function was f of x equal to the logarithm of the cubic root of x plus 2 plus the cubic root of x. So if I put minus 27, it gives me like cubic root of minus 27 plus 2 plus cubic root of minus 27, and I put here the logarithm. The cubic root of minus 27 is minus 3. Minus 3 plus 2 is minus 1. With the absolute value, it gives me the logarithm of 1 plus So this will give me cubic root of minus 3 is minus 3. So logarithm of 1 and minus 3 just give me minus 3. So the image of this point here is minus 3. Then I put the asymptotes, these asymptotes here. Okay, and remind that, look, the limit at the asymptote, it was minus infinity to the left side and minus infinity to the right side. So minus infinity to this side and minus infinity to the other side. Then the image of 0, if we put 0 in the function, we get log 2 plus 0. So the image of 0 is log 2. Log 2 is a positive number. So if I put 0, I will get log 2. So we are here. Then we have the point infinity, infinity, which is here, right? So the function start here. Let me use maybe the black pen. Start from this point, go to this one, do the relative maximum, and go down here. Then so it cover this part here. So we cover this part here. Okay. Then we start at the right of the asymptote and go straight up, passing through. Okay. We start like this, go straight up. Okay. Some questions, but probably there's something. We remember that this is 0. The function was not differentiable at 0. So here the graph should be not like this, but a kind of, I mean, this is not a big mistake, but can lose some marks. The function was supposed to have a vertical, so the function is something like probably like this. Okay, like probably like this. So it's something that the function should have a vertical asymptote in a vertical tangent in x equal to 0. But if you did it like we did before, it's not so that a big mistake, because we want a qualitative graph. So okay, then once this is done, the last question is okay, we define the function g of x given by this stuff. Okay, with alpha belonging to R. Okay, from the graph of f, C point D. So okay, trace a qualitative graph of g of x with alpha equal to 1 first, and then say if there exist values of alpha such that the function g of x admits a continued prolongation in x equal to alpha. So now that we got the graph of f of x, which is this stuff, okay, they give us the function g of x equal to, okay, x minus alpha over absolute value of x minus alpha multiplied by f of x. Please, what I want you to note is that this stuff here is nothing else that I don't know how. Look, that this stuff can, if x minus alpha is positive, this stuff will give 1. If x minus alpha is negative, this stuff will give minus 1. So this stuff is nothing else than the secant of x minus alpha. So please, this is the secant function. So so the secant of any quantity is equal to the quantity divided by the absolute value of the quantity. So it's important. So what they are asking you to do is the function g of x is actually the secant of the function x minus alpha multiplied by f of x. What does it mean? It means that this secant, the secant of x minus alpha, okay, But no, first of all, they want us to do it with alpha equal 1. So we can say that g of x is just secant of x minus 1 multiplied by f of x. But what is secant of x minus 1? So it means that g of x is going to be the same as f of x. Look, if the secant is 1, if this secant can be or 1 or minus 1. Yes or not? When we have secant of a quantity, it is 1 or minus 1 or 0. So, well, let's say or 0. It will be 1 when x minus 1 is greater than 0. Will be 0 when x minus 1 is equal to 0, and it will be minus 1 when x minus 1 is smaller than 0. This means that the secant of x, this is when x is greater than 1, when x is equal to 1, and when x is smaller than 1. Yes or not? So we get that the function g of x will be f of x when x is greater than 1. It will be 0 when x is equal to 1, and it will be minus f of x if x is smaller than 1. So just means that to draw g of x, this is the stuff. These are the possible situation. So g of x is equal to f of x, 0 and minus f of x according to these cases. Okay, so going back, we can just say that if x is smaller, if x is bigger than 1, so starting from 1, we have exactly the same f of x. So if we are starting from 1, okay, let me draw it a bit below. So I want to do the graph of g of x here. G of x is like this. So if this is 0 and this is 1. So if I am at 1, from 1 to plus, look, when x is greater than 1, g of x and f of x are the same. So the graph of g of x, it will be like, if I start from 1, I cut, it's this piece going up. Okay, so the graph, if I from 1, it will be exactly, so it's like exactly the graph of f of x from 1. So it's go like this. But at 1, g of if a g of x is equal to 0 when x is 0, so there is an open ball here, because g of 1 will be 0. This is 0, right? But now when x is smaller than 1, we have to draw minus f of x. Okay, when x is smaller than 1, we draw minus f of x. It means that for all these parts, this is the part when x is smaller than 1. Instead of drawing f of x, we will draw minus f of x. It means that where the function was positive, it was negative, it will become positive, and where it was positive, it will become negative. So if you draw it, let me put first the line minus 8. This was minus 8. This was minus 27. The f of x was like this. So if I am doing minus, it will become like this. Then this part, the other part was like this. Okay, and the minus of this part will become like this. So if I minus it, it will become something like the image of it will become something like this. Excuse me, the minus, it will be giving you something like this one. And open here. So the graph of g of x, okay, takes some time to understand, no problem, think about it. The graph of g of x is the one that I am doing in blue. this is the graph of g of x. This is the graph of g of x. Okay, exactly, this is exactly the graph that we need for g of x. Okay, nice. Excuse me for this. Okay, then this is exactly the graph of g of x. Nice. Now we conclude by the last question they ask is the following. The last question they ask is say if there exists value of alpha such that the function g of x admits a continued prolongation. Look, does it change anything if in this case the only thing that changed, okay, because I solved this with alpha equal 1. If I solve it with alpha equal 2, I will have exactly the same graph. The only thing is that if I want it, okay, if I want the new no, I will not have exactly the same graph, but because if I change alpha and I put alpha equal to 2, instead of having 1 here, I will have this kind of discontinuity at 2. If I put 3, I will have the discontinuity at 3. Is that clear? But imagine that if I cut it, like if we did it, for example, at 0, okay, if we take the function, if we did it when alpha is equal to 0, it will means that the function will be, we will have to do if we draw it for alpha equal to 0, it means that we are doing sine of x, secant of x, because alpha is 0, multiplied by f of x. So it will be the function g of x in this case will be minus sine, or it will be minus f of x when x is smaller than 0, and f of x when x is equal to, when x is bigger than 0. If you draw this function, it means that the function when x is greater than 0 doesn't change. The function remains exactly f of x when x is greater than 0, and it is like this. Okay, but before 0 it changes, right? No, excuse me. No, I wanted to show it, but by the way, I think there is no value of alpha for which this stuff will change. Okay, there is no value of alpha for which we will have continued prolongation of the function. There is no value of alpha for which we will have the continued prolongation of the function, because I wanted to prove it, but it's not so that easy to prove it. By the way, if you have any doubts, we solve all the function. If you have any doubts, please let me know, and we turn back on the doubts. Thank you.